Quantum materials, those exotic crystals and thin films that host superconductivity, magnetism, or topological behaviors, often dance to rhythms far too fast and subtle for traditional probes. Enter single qubit sensing. Imagine embedding a lone quantum bit, qubit, inside or atop a material, then watching it act like a tiny spy, feeling every whisper of magnetic fluctuation. How does it work? Researchers typically use a nitrogen vacation center in a single defect where a nitrogen atom sits next to a missing carbon. That NV center behaves like a controllable qubit whose energy levels shift with local magnetic fields. By initializing the NV spin state with a laser pulse, letting it interact with the sample's fast-moving magnetization, and then reading it out optically, you capture snapshots of fluctuations occurring in billionths of a second. Why is this such a breakthrough? Conventional magnetometers average signals over millions of atoms, washing out the fastest dynamics and tiniest defects. A single qubit, by contrast, sits right at the front lines, just nanometers from the surface, and can detect magnetic noise at frequencies up to gigahertz or even terahertz scales. Question: can we really see fluctuations that rapid? Answer: yes. By sequencing microwave pulses that flip the NV spin at precise intervals, dynamical decoupling, we tune its sensitivity to specific frequency bands, effectively turning the qubit into a spectral analyzer for the invisible quantum jitters of the material. What new insights can we gain? With single qubit sensing, scientists have tracked how microscopic magnetic domains flip in real time, watched spin waves ripple across thin ferromagnetic films, and probed emergent behaviors in candidate quantum spin liquids, materials where electrons' magnetic moments never settle into order. But this level of detail could reveal the secret timing of phase transitions, the birth of collective excitations, and the roles of impurities that make or break quantum technologies. Ultimately, by listening to the qubit's tiny screams, we learn to engineer quantum materials with tailored properties, paving the way for faster, more robust quantum devices and unveiling the hidden choreography of spins that govern tomorrow's technologies. Single qubit sensing is a quantum measurement technique where a single two-level quantum system, qubit, acts as a probe to detect external fields, such as magnetic or electric fluctuations. Unlike classical sensors, a qubit can accumulate quantum phase information about its environment, offering ultra-high sensitivity down to the nanoscale. This method exploits coherence, entanglement, and precise quantum control to measure weak interactions in quantum materials. Because the qubit is extremely localized, it can provide spatially resolved data about a material's internal dynamics. This makes single qubit sensors ideal for probing microscopic quantum systems in real time. Nitrogen vapor centers in diamond act as single qubit sensors to detect magnetic fields from nearby electron spins in a material. It's like using a single violin string to detect vibrations across an entire orchestra. Extremely sensitive and precise quantum materials, such as spin liquids, topological magnets, and strongly correlated systems, show dynamic magnetic behaviors driven by quantum interactions. These fluctuations can occur at picosecond to nanosecond scales, making them challenging to observe with traditional techniques. Understanding these fast-changing states is essential for uncovering novel quantum phases and exotic excitations like spin-ons or magnetic monopoles. Qubit sensing provides a non-invasive way to watch these fluctuations unfold in real time. This helps researchers map not just static properties but dynamic quantum behaviors. A single NV center placed above a quantum spin liquid detects rapidly fluctuating local magnetic fields as the system transitions between microstates. It's like placing a sensitive seismograph in the middle of a volcano to feel every microscopic quake before eruption. One of the breakthroughs of this method is the ability to track magnetic signals at extremely fast timescales, down to nanoseconds or less. This opens new doors to study non-equilibrium phenomena like ultra-fast spin relaxation, quantum quenches, and dynamical phase transitions. Traditional magnetometers like SQUIDs or Hall sensors lack the temporal resolution to capture these fast processes. By adjusting the qubit's coherence, time, and control pulses, researchers can tune it to sense specific frequencies. This selective, tunable bandwidth makes single qubit sensing a flexible tool for real-time quantum dynamics. Using pulsed microwave sequences, researchers modulate the NV center's sensitivity to detect gigahertz-scale spin waves in a ferromagnet. It's like tuning a radio to catch fleeting whispers from a fast-moving storm. Qubit sensors are particularly effective in performing magnetic noise spectroscopy, where they detect how the magnetic environment fluctuates over time. The rate at which the qubit loses coherence, dephasing, reveals the frequency content of the surrounding noise. This method gives a window into spectral density functions that describe spin interactions, correlations, and thermal fluctuations. Instead of merely mapping average fields, it characterizes the statistical behavior of quantum material fluctuations. This provides critical information for building quantum devices with minimal decoherence. Measuring the dephasing of an NV center yields the magnetic noise spectrum of a 2D van der Waals magnet under different temperatures. It's like listening to static on a radio to reconstruct what's happening in the room next door. Because single qubit sensors operate on the atomic or nanometer scale, they can map inhomogeneities, defects, or domain boundaries in quantum materials. This is especially important in 2D materials, heterostructures, and engineered quantum devices where bulk averaging fails to capture spatial features. Scanning techniques or arrays of qubits can build up high-resolution images of magnetic textures like skyrmions, domain walls, or vortex lattices. This capability turns qubit-based sensing into a quantum microscope. It bridges the gap between condensed matter theory and spatially resolved experiment. An NV-tip microscope scans a Cry3 monolayer and reveals localized ferromagnetic domains below the Curie temperature. It's like using a single grain of sand to draw a full-resolution map of a beach. Quantum materials often exhibit not only thermal noise, but quantum fluctuations tied to their ground state or topological order. These include fluctuations in entangled spin chains, edge currents in topological insulators, or critical dynamics near quantum phase transitions. Single qubit sensing is sensitive enough to distinguish these sources, enabling the study of fundamental excitations and symmetries. This is crucial for verifying theoretical models and discovering new states of matter. The sensor becomes a real-time observer of collective quantum behaviors. Qubit-based sensors detect magnetic noise near a topological phase boundary. In a Kitaev-like spin system, it's like detecting the heartbeat of an invisible creature hiding in a quantum jungle. Understanding and controlling magnetic noise in quantum materials is essential for scalable quantum computing and spin-based electronics. Fluctuating magnetic fields are a major source of decoherence in qubits and spintronic devices. By mapping these fluctuations with single qubit sensors, materials can be engineered for better coherence and robustness. Additionally, the method can guide design of magnetic tunnel junctions, spin filters, or memory devices. It transforms sensing from a passive tool into an active design strategy. Characterizing noise spectra of superconducting qubit substrates using embedded NV centers helps reduce decoherence in quantum processors. It's like tuning an orchestra by listening to each instrument's noise until perfect harmony is reached. Advanced quantum controls such as D-dynamical decoupling, Ramsey interferometry, or spin locking, allows precise targeting of frequency windows and noise sources. These protocols extend the coherence time of the sensor and isolate specific signals from complex environments. Tailoring these pulse sequences lets researchers probe different energy scales in the material. This makes the system not just a passive sensor, but an active spectroscopic tool with tunable resolution. It's quantum sensing with surgical precision. Carr, Purcell, MA Boomgill CPMG pulse sequences are applied to NV centers to extract spin bath correlation times in a magnetic substrate. It's like equipping a stethoscope with filters to hear only heart murmurs amid all bodily sounds. Single qubit sensing represents a paradigm shift in studying quantum materials, not just detecting fields, but decoding the living dynamics of magnetism at the nanoscale. It opens a direct path to observe transient, localized, and quantum coherent phenomena previously hidden from view. This method provides key insights for quantum device design, material discovery, and the foundations of condensed matter physics. As coherence times and spatial resolution improve, qubit sensors may become as fundamental to quantum material research as electron microscopes were to classical materials. It's sensing, but reimagined at the quantum edge. Future multi-qubit sensor arrays embedded in chips could perform real-time tomography of operational quantum circuits. It's like replacing a telescope with a quantum eye, seeing not just stars but the shimmering space between them,